Steam enters an adiabatic turbine at 80 bar. The steam expands polystropically with N equals 1.25. The discharge of the turbine is at 1 bar and is a saturated vapor. Determine the work output and the isentropic efficiency of the turbine. So we'll begin with our given information. And it's a good idea to draw a little sketch of this turbine. So the inlet conditions are 1, but notice the only thing we know about the inlet is that it's at 80 bar. So we only know one property at the inlet. The exit conditions, which we'll label 2, is at 1 bar, and it's a saturated vapor. So we know two things there. So that state is fixed, but the inlet isn't. The other thing we're told is this follows a polytropic process. PV to the N is a constant, where N is 1.25. So that's a summary of our given information. What have we been asked to find? First of all, the work output. Notice it's small w because it's kilojoules per kilogram. And B, the isentropic efficiency of the turbine. So our assumptions list. We'll start the assumptions list and fill it as we go. The analysis. So notice we're looking for the work of the turbine. So that's what we're trying to find. So let's start with the energy equation, and we're going to do open system, control volume, energy balance on this component. So as always, we start with our full energy equation. Rate of change of energy in the control volume is balanced by heat transfer rate with the surroundings, work transfer rate with the surroundings, plus a summation over all inlets of the mass flow rate at each inlet times the enthalpy, kinetic energy, plus potential energy, and then minus exactly the same set of terms taken at any exits. So m dot of the exit, h of the exit, v exit squared over 2, and g z of the exit. So here's where we start to make assumptions and build our assumptions list. So we'll be assuming steady flow. So I'll just say steady state here. Remember that this was described as an adiabatic turbine. So adiabatic, we'll say no heat transfer. So Q dot term goes to 0. And for turbines, the kinetic and potential energy at the inlets and exits can be ignored. So I'll say here KE and PE negligible. So that gets rid of both kinetic and potential energy terms. And the other thing that I'm going to do before I copy this equation down again is divide through by the mass flow rate. So there's only one inlet and one exit, so these mass flow rates are common. And when I divide this by the mass flow rate, I get the work per unit mass. So this becomes the work of the turbine is equal to H1 minus H2. So I'm using the numbering that I actually labeled my diagram with already. So we need to get these two enthalpy values to get the work. Well, we already know that point 2, the state is fixed. So let's go there and do that one first. So P2 is 1 bar, and it's a saturated vapor. So we can go straight to the pressure table, saturation table for water, pressure, which is table A3, and we'll get H2 is 2675.5 kilojoules per kilogram, and we'll get V2 equal to 1.694 meters cubed per kilogram. So H2 we've got. Now we need H1. The problem we have, of course, is we only have the pressure. We need another property. Well, the other thing we have going for us is we know this is a polytropic process. So P1 V1 to the 1.25 equals P2 V2 to the 1.25. So we can solve this for V1 to get an extra property at point 1. V1 will be equal to V2, P2 over P1, 1 over 1.25. So we already have these. Notice I looked up V2 while I was looking up H, and the reason is because I knew I was going to have to use it in this polytropic process to get another property at point 1. So this becomes 1.694 meters cubed per kilogram. The pressure ratio is 1 bar at the exit and 80 bar at the inlet. So all of this gives us a specific volume at the inlet of 0.050868 meters cubed per kilogram. So now we have two properties at the inlet, P1 and V1. So at P1 equal 80 bar and V1 equals 0.050868 meters cubed per kilogram, we can go to the tables and get H1 of 3732.6 kilojoules per kilogram, and while we're there, we're going to get S1 as well, 7.12193 kilojoules per kilogram degree Kelvin. And we'll see why we're going to need that in a moment. So now we can get our work for the turbine. Remember, work of the turbine is equal to H1 minus H2, and we have both of those now. So 3732.6 minus 2675.5 equals 1057.1 kilojoules per kilogram. So the work of the turbine, which is the first thing we were after, is 1060 kilojoules per kilogram. Notice my final answers, I'm rounding to 3 significant figures. So that's the work of the turbine. Now the other thing we need to get is the isentropic efficiency of the turbine. So remember, that's defined as the work of the turbine, which I've just found, divided by the isentropic work of the turbine, which we have yet to find. So this we can just leave as we have it. So we've already got a number for that. The isentropic work of the turbine would be H1 minus H2S. We have H1, we have yet to find H2S. Now remember, the significance of this subscript is that that's what the enthalpy at the exit would have been if the process had been constant entropy. So that's why, while I was back here at point 1 looking up the enthalpy, I also looked up the entropy. So we can now take a look at point 2S, and we know that S2S is equal to S1, which is equal to 7.12193 kilojoules per kilogram degree Kelvin. So there's our two properties, right? Because P2 is still equal to 1 bar. So we have an entropy and a pressure. We can therefore go and find enthalpy. Now it turns out that it's a mixture because this is between SF and SG. We can calculate the quality using this value of entropy, and the quality turns out to 0.9608. So that's coming from S2S minus SF over SG minus SF. These SG and SF values taken at 1 bar. And then we can turn around, take that quality, and get an H2S, and that works out to 2586.93 kilojoules per kilogram. So now we're ready to go back and complete this calculation. So the isentropic efficiency of our turbine is our work, which was 1057.1, kilojoules per kilogram divided by H1 minus H2S, 37, 32.6 minus 2586.93, both kilojoules per kilogram. And that works out to 0.92269. So we conclude by stating that the isentropic efficiency of the turbine is 92.3%. So we've calculated our work and our isentropic efficiency.